It's recording.
Okay. So we are opening today's discussion session, and we are very happy to have the Professor Katsushi Ito from Tokyo Institute of Technology. So he will give a talk on the WKB PBOs for higher order ODE and TBA equations. So please start.
Okay, thank you very much for introduction. First of all, I'd like to thank the organizer for giving an opportunity to give a short presentation here. I'd like to talk about my recent preprint that is appear last week in the archive. This work is in collaboration with Takayasu Kondo and Kohei Kuroda, who are graduate students of Tokyo Tech, and Honfei Shu. He's my former student. He's now in postdoc at the Nordita. So I'm going to talk about WKB periods for higher ODE. My plan of the talk is first I'd like to introduce some basic things about exact WKB analysis and ODIM correspondence. Then for Schrödinger equations as an example. Then I try to generalize the WKB analysis for higher order ODE. I'm not considered general class of higher order ODE, but kind of a special class of higher order ODE. And then I want to consider the relation between the y functions, which appear in the integral models, and WKB periods. That's my plan of my talk. So let me first a quick review of the exact WKB method for the Schrödinger equations, which was developed by Shibastone and Boros and thereby Dillinger Pham and Aoki Kawai-Takei and many others. So let me start from the Schrödinger equations with potential V and energy E. So we consider this equation in the complex plane, and H bar is also regarded as some certain complex parameter. So we want to know the property, part-additive or non-part-additive property of these solutions. So the standard WKB ansatz, we assume the solutions to these equations is like this exponential form, and the Q is expanded in H bar. So then substituting this WKB ansatz to the Schrödinger equation, we'll get the Riccacci equations, where P is represent the classical momenta of the systems. Then substituting expansions into these Riccacci equations, we'll find that Q is divided into the even power of H bar and odd power of H bar. And odd part can be represented by the even power series of Q. Then, essential part to be investigated is the P, and the odd power is forms the total derivative. So then we introduced the concept of the WKB curve. And then we can define the period integral on this WKB curve and define the WKB period. But this is a asymptotic series in H bar. We need to make a Borel summation of this period to investigate analytic properties of WKB period. Then employing the exact quantization conditions, we'll find the exact spectrum of these Schrödinger equations. So that's a brief story of the exact WKB method. But we have a little bit another story related to this second order differential equations. So this is a ODE correspondence, which I want to describe a little bit. So it was firstly proposed by Dore and Tateo, I think in 1998. So they found some relations between the spectral analysis of the ordinary differential equations and function relations of certain two-dimensional quantum integral models. So they first consider this correspondence starting from the Schrödinger equations with monomial potentials. That means the is a single term with power 2 times m. So 2 times m might be we think it's an integer. So m can be integer or half integer. So, but it's kind of some notations. So we then consider the Schrödinger problem of this with potential, monomial potential times with also energy. Then so we can seek some asymptotic solutions for this differential equations. That the main object we are when we are connecting these systems into the integral systems. So the first so yk I denote the labeled by integer, which is a asymptotically decaying solution in some region in complex plane. For example, along the real positive line, you can find the asymptotically decaying solutions, which is uniquely defined in these regions, like this. Then, but it's can not it doesn't show a decaying property for other angular sector. So so Y0 is unique in these angular sector regions. So to find the decaying solutions along, for example, this another sector, we do the rotations of the parameter by the phase factor omega. Then we can construct systematically the asymptotically decaying solutions. We sometimes call subdominant solutions in the each region.
Sorry.
Yes.
So this picture is Stokes graph of this system?
Not really a Stokes system, just Stokes graph will be much more complicated around
Yes.
the finite region. But just showing the some essential point is the much larger regions on the complex plane. But we don't care about this structure of the origins at this moment.
Okay, thank you.
So in the exact WKB analysis, the solutions is expansion of this solution is a most important object. But in the context of ODIM correspondence, the most important ingredient is the Wronskians of the solutions. So then this Y and the set of the subdominant solutions, subsequent subdominant solutions, says YK and YK plus 1, forms a basis of the distributed solutions. Then one can construct the Wronskians for these solutions. Then if they are not linearly, they are linearly independent, this Wronskian does not vanish. So under some choice of this combination of the Wronskians shows that they are not vanish at some particular values of the choice of the pair of the solutions. Then one can define, and also I must say that this Wronskian is independent of the coordinate of the ODE. Then this is simply the functions of E. So I denote this function as the YSE, which turns out to be one Y functions of certain integral systems. And this Y functions shows that for very large parameter E, they behave asymptotically exponential to the some functions of energy. So exponential factor is just proportional to the classical periods of the systems. Here, I take this example of some cubic potential. So we can take some WKB curve becomes the torus. So we can take the two independent homological cycles on this complex plane. And also, this combination of Wronskians satisfying by using the so-called trivial relation satisfies the set of determinants. One can show that this Y function shows that this functional relations. So this is called the Y system in the context of the integral models. Then two conditions. One is the asymptotic behavior on the Y system. One can transform this Y system into the set of the integral equations. So this is called the thermodynamic Bertrand equation that we want to seek for the higher order ODE cases. So physically, in the context of the two-dimensional integral system, this logarithmic of the Y function represent the pseudo energy of some K-side particles of certain integral field theories. So this TBA equation determines the self-consistently the asymptotic energy due to the interacting each other. So phi SS prime describing the interaction between the pseudoparticles of the effective integral field theory. And one can extract, get the information of free energy from this TBA equations. Then for large size of the system L, you get the effective central charge that describe the field theory described by these TBA equations. Then it turns out this we can extract the central charge from the free energy that we can identify this field theory is just the Virasoro minimal models of non-unitary type. So this was kind of correspondence was developed also by Zajanov and Lukyanov Zamolodchikov many years ago. So in my collaboration with Marcos Marinho and Honfei Xu some years ago, we argued that the correspondence between the ODE, Schrödinger type ODE and Y functions. So we, by investigation, including some numerical works and investigating TBA equations and WKB analysis, we find that correspondence of two objects appearing in the exact WKB and integral models. So that means the our observation is that Y functions of the integral systems there's Boros symbols, which is the exponential of the Borel resummed quantum period is exactly the same as the Y function. We investigated this phenomena for generic polynomial potential. We show that they're the same asymptotics and also share the same discontinuity. So TBA equations are related to this general polynomial potential is given like this. So each pseudo energy is associated with the cycles represented by the intersection of the potential of the energy. And for each cycle, one can associate with the mass term corresponding to the classical period integral associated with these period on the WKB curve. And then studying these integral equations, one can recover the structure of the exact period of the appearing in the Schrödinger equations. So we are going to generalize to some extent this phenomena to the higher order ODE that I want to explain a little bit. So WKB analysis for higher order ODE has a long history. So starting from the Burke, Narbins, Roberts, and also there's some very good textbook of the by Honda, Kawai, and Takei. So they discuss kind of general class of the WKB analysis for higher order Schrödinger equations. But in this talk, I like to very specific type of the higher order equations. just obtained by replacing the second order derivative by the higher order derivative term. So say R plus 1 order derivative. R is from 1 to 1, 2, and 3, and some integers, positive integers. So maybe you think this is very specific, only very special generalizations of the higher order ODE. So I'm not quite sure but what kind of physics are related to this in like a Schrödinger equation. I'm not sure what kind of physics appear related to these equations, but so this kind of ODE appears in the context of as a certain origin has some classical integral systems. So the first these equations coming from the certain limit of the linear problem associated with the affine to the field equations. So that's affine to the equation takes the some flat connection form of two connections. One is the two gauge field connection AZ and AZ bar, but the conformal limit, one just take the homomorphic part by taking certain limit. So this is kind of this set of linear differential equations. And for AR type and the fundamental representations, we can derive the higher order differential equations. The first component for this set of linear differential equations, you'll get the higher order differential equation from these ones. So this has some origin in the related to the Lie algebra. And also it has related to the quantum Seiberg-Witten curve of some particular type, ARAN Argyles-Douglas theory. Here, in this case, the epsilons is not regarded as a complex, is not regarded as a Planck constant, but it's certain omega background parameter appearing in the Nekrasov-Saakashvili limit. So that's a temporal reason I want to consider this equation. So this contains the example of the second order equation. Let me try to work out the second from the second order ODE as an examples. So as we explained before, so we assume the WKB ansatz, and S is expanded by epsilons, and we would have Riccati equations for this second order ODE, and one can solve these Riccati equations recursively, and we can determine the higher Sn like this. So, and S0 and S1 and S2, and S1 is always take the form of the log of a derivative of the log S, S0, S0. And from these simple properties of Riccati equations, S0 every term is shown to be total derivative form. So we do the analysis. We can consider some WKB period as the even power of this contribution. Then we assume that Px is a polynomial in X. So this hyper WKB curve defines a hyperelliptic curve of certain genus. And one can, on this WKB curve, one can take the basis of the meromorphic differentials like this. And the first G ones becomes the holomorphic, which corresponding to the genus of the this WKB curve. And this is the set of basis of meromorphic differentials. And one can also introduce generating functions of this set of bases. This is called, I'm not mathematical terminology, I'm not sure what it should be say. But in the context of gauge theory, it is called the Seiberg-Witten differentials. So that means if we take a derivative with respect to the moduli parameter u, we get the set of these basis of meromorphic differentials. Then one can express these higher order terms expanded by the this set of meromorphic differential up to total derivative term. Then we get the higher order correction to the period can be expressed by the from the classical period by acting certain differential operator acting on the with respect to the moduli parameter. So from this relation we can calculate the higher order correction systematically, and we temporarily call this differential operator as a Picard-Fuchs operator. So now let us extend our analysis to the third order differential equations. So this we just take the same ansatz as the appears in the second order case. And so then we will have Riccati equations. It's like much more complicated of the cubic in S. So looks like complicated, but we can solve this Riccati equations term by term recursively, and we'll find this kind of set of a series similar to the second order differential equations. So I'm not, I do not have a complete mathematical proof for this the whole series, properties of the whole series, but as far as investigated by using Mathematica, so I can observe that this, as in the case of second order case, S odd is always becomes a total derivative. And something new appearing in the third order differential equations is that the this some term in even becomes also total derivative. So in this case, third order differential equation S4 and S10 and others becomes total derivative. That's a very new things appearing in the third order differential equation. So then the WKB curve for these systems is the y to the cubic, cube y is equal to some polynomial in X. So in mathematical literature, it is called the super elliptic curve, not a hyperelliptic. So, and one can see the basis of the meromorphic differentials, which is appear in the textbook of Riemann surface, famous textbook of Farkas-Kura. So one can find a set of basis meromorphic differential is given like this. The first law is already appears in the hyperelliptic, but the this is a new appearing in the third cubic super elliptic curve representations. So associated with this two set of bases, one can introduce two generating functions for this meromorphic differentials. Then similarly, one can construct the expanding the quantum corrections by the these bases. One can construct the Picard-Fuchs operator from the classical periods that we can do some explicit example for this third order differential equations. And also the mathematical observations tells us that for general R+1 order differential equations, we can perform this analysis to, in general, to some extent. And we have a set of, assuming the WKB ansatz, we'll get the Riccati equations for this R+1 order differential equations. And the series can be computed by the like this. So if you choose the R equal 1 or 2, you will recover the previous result of the second order and third order equation. And observations is like the second order, the third order equations. The S odd is always total derivative, and some other terms also becomes shown to be total derivative, which is the related to the Coxeter number of the AR the algebra. So we find that this for this number 2h and n is non-negative integer plus h plus 1, it becomes a total derivative. Then we can also generalize this concept of WKB curve, which is also the super elliptic Riemann surface, and take a basis of meromorphic differentials. And one can also construct the quantum corrections from, which is related to the classical periods by differential operator, Picard-Fuchs operator. Then, so one can compute to some extent the differential operators from here. But we are not going to, at present, we are not investigated fully general potential, polynomial potential term. We are just restricting to the case our consideration is for the specific potentials. That means quadratic potentials. So this is this super elliptic curve, just R+1 sheeted cover over the complex plane with two branch points. But if you representing this curve in terms of x by y, it's just becoming a hyperelliptic curve. So we know how to do it for the so then we can sometimes easily work out for this quadratic potential cases. And one can see the sheeted cover of the representation of this curve also related to the double cover with 3 branch points, so which is related to each other. Then in this case, one can compute the classical period from the definitions. Then it turns out you can use the beta functions and extra phase factor, which phase factor and sign, which is coming from the one seat we choose. So more systematically, the such computation of the contour and for more general potential is, I think it's done by the Knightsky and Holland Knightsky and Dumas Knightsky. But just simply considering the quadratic potential, then we can work out explicitly for these cases. So the remaining part, I will discuss the Y function constructed from this higher order ODE. So it is more or less standard in the previously worked out by Dre, Dunning, Tateo, and Junji Suzuki some years ago, many years ago. And so just explain how to construct Y functions from this ODE. So just I said in the Schrödinger case, we start from the subdominant solutions and taking geometric rotations and taking forming a basis of the solutions. Then we construct the Wronskians for these solutions. So labeling is a little bit complicated. But by appropriately choosing set of the set of a basis, one can construct the T functions. So we'll get a T system associated with this. And taking some ratio of the T function, we'll get the Y functions. So, and then it is satisfy the so-called ARA type Y system. So so we have a set of the AN type linking diagram connected by so set of R AN type linking diagrams connected like this way. So this defines describes the integral system associated with the this higher order differential equations. Then so quadratic potential cases, we just have a single column linking diagram stretching the vertically. So this again define the A-type Y systems. Then one can investigate the where the sorry, this is +1 denotes the shift of the spectral parameter theta, where the epsilon is represented by theta exponential minus theta. So and so this representing some geometric rotation for this system. And one can also investigating the large theta or small epsilon asymptotics for this. And M is the represented by the classical period. Then we can get the from these Y systems and asymptotics, and also assuming the analysis, and we can get the TBA equations. So this is exactly the same equations for the A-type TBA system appearing in the Schrödinger equations with monomial potentials. And the kernel functions is characterized by the Lie algebra, G representing the incidence matrix. Of AR type. And actually this system describing the integral theory. So, and this kernel functions is also represented by the corresponding to the some certain S matrix of the affine to the field theories. Then we have another expression for these kernel functions. Then we can expand these kernel functions in terms of large theta. So then we'll get the large theta expansion of the Y function from the expansion of the kernel functions. So then this coefficient of the expansion of the Y function is represented by a variable from the R. So R is, sorry, I forget to define here. So this is defined by this, and if once we get the profile of the Y function by solving these equations, so we can calculate this expansion coefficient of the Y functions. So then my proposal, which was done, claimed in the my recent paper, is that for this quadratic potential, the Y functions is under WKB period as following relations. So we like to confirm these relations by explicitly by numerical calculations. But these relations implies by expanding epsilon in epsilon, both left-hand side and right-hand side, we'll get the expansion coefficient satisfying these relations. So the interesting point is that we can see from these expansions, I forget to say, but is the expansion coefficient here is there are some vacancies. So if n is mod h, so it turns out this coefficient vanishes, which coming from this expansion of the kernel functions. So it turns out these conditions, vanishing conditions, if we interpret it, if assume this identity, it turns out this vanishing condition implies that the vanishing condition for the expansion of the WKB period as observed by investigating the WKB series for higher order DE. So it is supporting these conditions. Both vanishing conditions are supporting these identifications. We also check this correspondence by explicitly checking evaluating the period, and also Y functions numerically. So this is the case for the third order ODE with this potential. And it will numerically, this is shown to agree very well in each other at higher order. So we can say for this higher order systems, the Y functions is represented by the WKB period, both symbols. Correspondence are likely hold for higher order ODE. So this is, I'll have time to conclude. So we have studied the corresponding for the higher order ODE and TBA equations. And actually TBA equation describing the conformal field theory, which has a W algebra symmetry. So we can also think the Y functions, one can relate the Y function and the integral motions appearing in these W minimal models. And also just maybe it is interesting to discuss some Borel summability and the discontinuity formula for higher order WKB periods. And also for generic potential, we have a problem of the word crossings. And it is nicely to check this WKB. We have seen the duality between AR AN and the AR ODE relations. So which has also appeared in the context of Algestag's theories. And also we can generalize to higher order ODE associated with the other types of D algebra. And also interesting to the apply to the SUN Seiberg-Witten curve, quantum Seiberg-Witten curve for higher order rank. This paper deals with SU3. Okay, thank you very much. So that's the end of my talk.
Thanks so much, Ito-san, for the very exciting and beautiful talk. So now we are going to open the session for the questions and discussion. If you have questions or this or some comments, so please. Okay, so we have got the comments from Andre also. Could you see, Ito-san? Could you see the chat from the
Yes,
Andre?
I can see. So
Okay.
let's back to the page. Okay, yeah. So on the both question is integral models corresponding to the Schrödinger equation with generic polynomial potential. So we think this is we have the similar beta and the TBA equations for we know some similar integral models associated with this type of TBA equation. It is called the homogeneous sine-Gordon models. Which is, I think this is higher rank version of this paraphenometric theory. So in the case of SU n equal 2, this is becomes sine-Gordon models. So this is a kind of a higher rank generalization of the sine-Gordon models, which admits this kind of TBA equation, set of TBA equations. That I know at this moment.
Can I ask just a follow-up
Yes.
question a moment? Sorry. So is it the case that is that any particular type of algebra associated to homogeneous sine Gordon models, or all you'd be able to do to include all homogeneous sine Gordon models here?
Yeah, it's actually it's a kind original homogeneous sine Gordon models which have some this TBA equation that the driving term is this is the massless type driving term of the TBA equations, and also so one can change this driving term into the massive driving term, and one can also introduce some well, I forget the name, but some extra parameter which makes a boost of the which changes the mass parameter a little bit. So this equations is from the original TBA equation of the homogeneous sine Gordon models by restricting by taking a scaling limit, a conformal limit of this massive type TBA equations, and choosing the extra parameter by some appropriate ones. And
But so-
actually, it extended to the complex regions, so it's kind of a little bit generalized ones.
So this is specific for the massless sector, so the particles
Yeah.
in homogeneous. But there are some generalizations where you can include to the similar analysis and can include the massive sector, or do or analyze the massive sector.
Well, it's another story of the massive version of the ODIM correspondence. So we start from the massless ODE arising from the massless limit of the affine to the equations. So if we start from the original affine to the equations, we can introduce some two variables, holomorphic and anti-holomorphic. So this two set of equations define the producing the massive dispersion relations. So in that case, we need to consider some massive version of the ODM correspondence to really study the TBA equation for the massive type homogeneous sine Gordon models. But I do not actually go into that directions. But I'm very interested in that analysis.
But have you looked into, meaning you haven't directly studied, but have you looked into it? How meaning I looked into it at some point, and it looked a fair amount more complicated, and I was just wondering what.
Yes, I agree. Yeah.
So okay.
So we just set up two differential equations, but it is related. It is compatible. It's satisfying the integrability conditions. So that we can study the asymptotic solutions and can construct some quantities appearing in the integral models from that set of differential equations.
Okay.
for affine to the cases. Actually, it's a similar equation appears in the study of the ADS CFT correspondence. The string theory on the ADS 3 space describes the such a massive type sine-Gordon, homogeneous sine-Gordon models, which was studied by the Aldai, Sava Vieira, Maldacena.
Thank you.
So I want to confirm some points on this identification between the Y functions and the WKB period. So regarding this, how to say, conjecture of the correspondence, so you have already checked the leading order analytic facts between them. And,
yes.
Okay, and you did the numerical checks between them in all orders or
Yes,
higher.
to do that, I need to do the Borel summation of the WKB pairs, but it's we can compute higher order terms arbitrarily, but just I didn't do the further approximation and Borel summations. That's next task, but I didn't yet do yet.
I see. Okay, thank you. Please feel free to ask questions or give comments.
Can I ask another
possibly
dumb question? Sorry. I would rather have this question out of the recording, but so meaning there's different numerical methods, right, to solve either TBAs, Y systems, and exact quantization conditions. And from your experience, meaning given that there's this relationship, which one would be the typically your preferred way, or if depends on the problem or something? So to actually, for example, analyze more specifically Stokes phenomena, or to have an explicit solution at the end, because a lot of these, especially TBA, Y systems, meaning they have a solution, but it's implicit, you still have to solve it. So from your experience, which
so if you like the ODE and integral equations, if you prefer which prefer you that things if we use deep integral equations, we can find some numerically it's very useful to calculate, and so it gives another tools to work out the Borel summed quantities from that kind of equations. And maybe it gives a complementary informations of the integral equation approach, and this dimension approach gives some complementary role for the analysis of actual problems. Yeah, I hope this both are good, provides a good method to analyze the problem.
Thank you.
May I ask one question?
Yes.
It seems that for instance, taking Schrödinger type of equation, the potential as well as boundary condition seems to be corresponding to the case of bound state problem. But in Schrödinger type of equation, there are also scattering type of problem, I suppose. Yeah. So is this method applicable to that situation as well?
Well, that's problem of the Schrödinger equations, solution of to the Schrödinger equation is appropriate boundary conditions, which are not, this is I think this is somehow the another input imposed on the WKB, exact WKB period. Mm-hmm. So sometimes we can have the informations of the, for example, tunneling coefficients and other quantities. But I'm not quite sure what the full information about scattering can be extracted from this this analysis.
I see. So yeah. In other words, may be applicable, but with some modifications. Is it the way? I see.
Yeah.
Okay, thank you very much.
I have a question.
Yes.
So, okay, in this slide, you determine each Stokes sector by asymptotic property at infinity region. So,
yeah,
when we consider periodic potential or elliptic function as a potential term, then how do you define each Stokes sector?
Yeah, that's the work related by this some recent paper on the this kind of approach to the Marshall equations. There's some paper appears. So I'm not, I cannot remember the details, but you can, I think they discuss some the behavior crossing the Stokes regions to get the discontinuity formula to get the TBA equation associated with that related to the Marshall equations. Yeah. But I maybe, I cannot explain this. Sorry, I cannot explain this kind of setup here.
So just writing Stokes graph as order method, I mean, consider the imaginary term of the reading order of WKB expansion, and just write Stokes curve. And also it defines the Stokes region, I think. So is it, I think it's sufficient to consider this problem, but why do you consider this way? I mean, asymptotic or behavior at infinity.
Yeah, that's the simplest setup for this potential. So something happens at the infinity, and if you add angular momentum, something special happens at the origins. So we just simply consider the behavior at the infinity for the polynomial potentials. That provides a simple setup for solving this constructing TBA system from that ODE. So the other periodic potential give rise to a little bit more complicated asymptotic structure or some potentials structure. Maybe discussion will be a little bit complicated compared to the polynomial cases.
I see. Thank you.
So there's another comment by André Voros.
So comment to Professor Sakai.
Which is one, proper scattering solutions require non-polynomial potentials. And two, in complex WKB approach, the bound state problem formally looks like a scattering problem with free waves replaced by leading order WKB waves. And the just function is a primary resurgent function in 1/h bar. Yes, it begs, sorry, the question of so what happens if we how far can we go from polynomial potentials?
Well, yeah. So it is essentially the just working on the it's sometimes my iPad disconnected, so maybe it's closed my connection. Yeah, and it is essentially the structure of the wall crossing. The problem is just the wall crossing phenomena for such a higher rank TBA equations, and to some extent it was studied by the work by Guy Ottomu and Naitsuke. So then I have no essential problem to work out for studying the generic polynomial for higher order cases. But a little bit non-trivial cases to add the other derivative term to that equations. So that's a similar cases appearing in the paper by BNR and studied by the appearing in the Honda Kawai Takei, the textbooks. So I'm not quite sure what happens, some serious problem for that general higher order ODE cases. So I'm wondering what happens for that generalized cases.
I guess my question is, have you tried anything that's just a slight perturbation from the polynomial potentials or something?
Yeah.
Or already doing that kind of?
Not yet. Just I just finished my paper last week, so just trying to generalize it from now. Yeah.
Okay, thank you.
I may have missed the one of the important results, but so based on your conjectured correspondence between Y function and the WKB periods, so did you find the structure of the Borel plane? So I mean so where the Borel singularity exists, or the Borel summability or Borel non-summability of the third order Schrödinger type equation. So
yes, from the Y functions, in viewpoint of Y functions, it can be characterized by the integral equations. So we can find where the singularities appearing in the Y functions. We can identify the location of the singularity in the Borel plane from the integral equations. But it's WKB analysis, it's not clear to me where it is. That should be studied further. Yeah, that point. But I just compared the two objects at the formal level, formal power series, asymptotic series expansions. That's a claim in my paper.
At least if we believe that correspondence, so we can speculate where the singularities are.
Yeah, that's right. Yeah.
In the case of the third order Schrödinger type equation, so is it Borel summable?
Yeah, I think so, yeah. Actually, yeah, I want to know how to treat these series mathematically to prove the Borel summability. Yeah, that's the problem. Yeah, to be explored further.
Thanks so much.
Shall I press recording off and have the opportunity of less smart questions? Okay, will do.
So, do you want to